Going to talk you through our energy lesson. I'll probably do this in two chunks. From what you learned about before, there's a definite connection between work and energy. Sometimes I'll say they're almost synonyms. If you do work on an object, then that object gains energy. We're going to use that idea today. And if an object has energy, that means it could do work. And when we say work, usually work means the ability to put a force and make an object move. There's lots of kinds of energy. You've probably brainstormed them over the years in your elementary science and potentially other science courses in high school. The two that we're going to focus on for now in grade 11, we'll add a third one later, is what I call gravitational field energy and kinetic energy. Sometimes it's called gravitational potential energy, but there's kind of a shift to start calling it gravitational field energy because it's about the gravitational field. The first little part of this is we're going to do a couple little proofs to get equations. And then once we get equations, you need to be able to use the equations. So videos embedded in videos. I'm going to talk you through what I've typed here, but there are videos of the proofs as well that you could watch just to see how the proof comes up. The first one isn't too bad. The kinetic energy is a little bit more complicated, so you can watch those other videos just to make sure it clicks. But I'll never ask you to memorize a proof. I won't ask you to regurgitate it. You should be able to read through it, and it should kind of make sense to you, but you wouldn't be expected to come up with these on your own or to memorize them. Okay, going to start with gravitational field energy. Simply put, the farther something is from Earth, the more energy that thing could do if it were to fall back to Earth. So as an example, if a bowling ball rolled off a table and landed on your toe, it would do a little bit of work on your toe. But if the same bowling ball fell off something higher, since it's in a higher position in Earth's gravity field, it could do more work when it landed on your toe or whatever it lands on. So the higher something is, the more energy, the more work it could do when it landed. We can get an equation. Sometimes it's called the work energy theorem. We say that the work done to do something, in this case we're talking about lifting, the work done is equal to the energy gained. That's a kind of a philosophical statement, but what's powerful about it is we have an equation already for work. So if the energy gained is equal to the work, we can say that the energy is equal to the work equation, FD cosine of the angle. There is a video linked in here somewhere with the proof. Oh, there it is down here. You can watch that video, but rather quickly, we can say that the force just has to match gravity, so that's mg. The distance we're going to call h since we're lifting at a height. And if we lift it straight up, the angle is 0. So our FD cosine of the angle turns into mgh. Cosine of 0 is 1, mg times h, we get the mgh. I'm going to put a lowercase subscript g. Energy is not a vector, so that's a scalar. E, capital E with a little g, stands for gravitational energy, and it's equal to mgh. The video for the proof of just me talking about the proof is there. You can watch that one to help make it click. And perhaps, I'm going to keep rolling, but maybe you want to pause this video and try those two examples. I'm going to talk about kinetic energy, then stop this video, and you can look at whatever you need to, but I'll keep rolling on this particular video before I hit stop. Gravitational energy was related to height. Kinetic energy is related to speed. If the bowling ball was rolling slowly and bumped into you, it could do a bit of work on you. But if the same bowling ball was moving faster, when it bumped into whatever it bumped into, it could do more work. So logically from that, faster equals more work equals more energy. We're going to use that work energy theorem again. The work done to push something and get it moving, that equals the energy that it gains. So since work equals FD cosine the angle, the energy is FD cosine the angle. This proof is a little bit more complicated. I'm going to go through it a little bit quickly here, but you do have this link down here to watch it a little bit slower. We're working with FD cosine the angle. We're going to replace F with MA. The angle we're going to replace with 0 degrees. So our equation FD cos x becomes MAD cosine 0. The cosine 0 is just 1, so we get MAD. Now, a little bit of math trickery. If we go back to kinematics, we've got an equation, the equation that doesn't care about t. It's the difference of squares 1. If I sub in that the first speed is 0 and the second speed is some arbitrary speed, call it v, When I rearrange, I can get A times D equals V2 squared, or sorry, just V squared over 2. I'm choosing to get A and D together to make a substitution, because back up here, I said energy was M times AD. Down here, I'm saying AD is V squared over R. When I substitute, I get this, or when I add the K, I'm going to call it kinetic energy, and it's 1/2 mv squared. That's a quick talk through on the proof, but again, watch this video linked in italics, and you can see me doing that proof a little bit slower. At this point, I'm going to pause this video, but what you should be doing is try these gravitational questions up here, try these kinetic questions here, and the worksheet that's linked, you can do the first part of it. I'm going to pause this video, then I'll talk you through the next portion of this energy topic.